Hi everyone, welcome to Under the Microscope. My name is Pranoti and I'm your host. Under the Microscope is a podcast where materials and nanoscientists are featured, and we are in the sixth season at the moment of Under the Microscope. We have the third guest of our season six, and I'm very happy to introduce you to our guest today. But before I do that, make sure that you are subscribing and you are following this podcast wherever you're listening, wherever you're watching. This is absolutely free for you. It doesn't cost you anything, but it means a lot to us. So thank you very much. Thank you for your support. Once again, I'm Pranoti, your host, and enjoy today's episode. So today we have with us Tobias Heindel, who is leading a group called Quantum Communication Systems at the TU Berlin, Technische Universität in Berlin in Germany, and he's the group leader of Quantum Communication Systems. Hi, Toby. Welcome to Under the Microscope. How are you?
Hi, Pranoti. Thank you very much for the introduction. It's great to be here.
When I was recording a few weeks ago with Doris, who is also our colleague, so to say, that we are working with for the Quantum project, I also mentioned to her that it's very strange to record and have this kind of a conversation because we have been talking for the last few months, and this is the first time we are recording our conversation. It's just a little strange also to call you Tobias Heindel because for me you're Toby. So Toby, your research group is working on quantum communication systems. Could you please explain what that means to our listeners and watchers? Please explain your research in super simple words.
Yes, thank you, Pranoti. So what we are doing is we generate single particles of light, which we call photons, in a very technologically involved fashion. And these we use to encode information, quantum information in their state and transfer them between two parties, entities, for instance, people which want to communicate with each other. And by using fundamental laws of quantum physics, we're enabled to do this in a ultra-secure fashion, such that it's actually provably secure, not only based on computational complexity, which is the case for the encryption we are currently using, for instance, for this video call. And these systems we basically develop from the single photon generation part over putting things into boxes and make it more practical up to the implementation of these quantum communication protocols.
Right. So okay, so many questions. I have so many questions which I could not ask Doris as she is a theoretician, but you're an experimental scientist. So okay, quantum internet, secure communication, quantas or photons, single photon source. There were a bunch of new things for me as well. So how do you do that? Is it like do you develop a chip? Is it a material or is it a membrane that makes the communication? How does that work? Because internet is something that I can't hold in my hands, right? So it's hard for me to imagine what exactly is it. How exactly do you do it? What are these building blocks? Tell me that.
Yeah, sure. So if we look at the device which allows us to generate these single photons, then it can be a chip which we are processing in our clean room with collaborators which are growing devices for us, and we make then actual practical devices out of it in our clean room. And I could tell you now about that these chips have single artificial atoms inside. That means although the material, the chip is consisting of many atoms, there's some tiny nanometer-sized structure inside, which acts like an artificial or basically a natural atom, which is isolated. A single atom that can emit light, as we know.
Wait. You lost me there. What do you mean by isolated atom, and what do you mean by artificial? I was with you until the chip.
Yes, I
There is
understand.
the chip.
So
Then yeah.
we are basically using semiconductors. That means
Mhm.
we have electrons and holes, and usually if we put them inside the semiconductor, these electrons and holes, they can move all around. But to get quantum light, we need some confinement. That's like a small box where we put electrons and holes inside. And if we have this, then the electrons and holes can only access discrete energy levels, and then they can recombine by emitting a single photon, for instance.
Right. Quantum
Most
light. Sorry, quantum light. What color is the quantum light? Can I see it? What is like? I know light. I know laser. I know the yellow, blue, green light. What is
That's a
quantum
good
light?
point. So let's compare it maybe with a light emitting diode, LED, which you know from your handy smartphones and so on, or your flashlight. And you now you switch it on. And in our case of a quantum LED, you would not see anything because it's single photons, which have a very low intensity because it's single light quantas instead of a flashlight where you have millions of photons if you switch it on. And when
Don't
you actually, we can make it at various colors. We can have light from, in principle, from these artificial atoms, which is in the visible range. We are working a lot on wavelengths at 900 nanometer wavelength. That's near infrared. But we are also working on telecom wavelengths at 1300 and 1550 nanometer. That is very important, the latter, for if you think of optical communication in fibers, in glass fibers, then you have the lowest absorption loss at the longer wavelength, telecom wavelength. That's why we also have quantum light sources emitting there.
Okay, so so the visible is like I think 300 to 700, something like that.
Yes.
That is the
Yeah.
visible range ish, sort of. And you can also make quantum light in this visible range, but then the quality will be worse. They will be slower in performance, in information. Is that what you mean when you say that at a higher wavelength the absorption is lesser?
It's more about simply about the loss. If we speak of free space optical channels, so communication can happen not only in fiber optical cables, but also
Mhm.
in free space communication. And that depends on the application you think of. There are experiments in our field where satellites are used for optical communication, and then you have to see which molecules in the atmosphere absorb light a lot. Then
Okay.
you should use a quantum light source, which is emitting at a wavelength where there's not a lot of absorption. So we can actually have a reasonable number of photons detected at the satellite or at the ground station. And same for optical fibers, which we are using in city networks or between cities. They have a certain spectral characteristics, and that characteristic shows us that we have high absorption losses at shorter wavelengths, and the minimum of absorption losses is at 1550 nanometers.
Uh-huh. So I think in Germany now, since a few years at least, we in some parts we have the optical fiber for faster internet and all of that. So do you know which range, which wavelength range are we talking about? If we have, let's say, internet or the Wi-Fi basically that is coming in my flat, for example, what is the wavelength are these optical fibers
So
working at?
Wi-Fi, of course, is something different, right? There you have a transmission basically here within a local network in your home. But
Right.
the optical fibers, basically, if you have a fiber to the home, then it is also 1550 nanometer, 1.55 micrometer wavelength, which is the communication.
Uh-huh.
That
But
this
then, yeah.
Actually, telecoms people are talking of the telecom C band, so it's not a a single wavelength, but you have a range of wavelengths, which is called C-band, and this is subdivided in tiny spectral channels, which are used then for the internet.
But then if we already have optical fibers at 1.5 micrometer wavelength, why do we need, like, what are the advantages of using the quantum light then? What is the benefit there? I mean, we have optical fibers. What is working? Why should we go for quantum internet light stuff?
So the problem is currently they use bright lasers for communication. So if you unplug the fiber optical cable, then you see bright pulses. That means there are a lot of photons in these pulses, and there are videos in the internet. You can easily access those fibers by opening channels, and then you can pick some of the photons and get information which is transmitted in the optical fiber. That's called in our language eavesdropping. So some person Eve picks some photons, which is called photon number splitting. And then you get information of the communicating parties. And even worse, the people communicating with each other, like we do currently, they do not even recognize that someone took some of their data and knows about the message they exchanged. Now, if you use single quantas and the light source, which only emits photons one by one, then you can obviously also pick photons from the quantum channel, but then Alice and Bob, the communicating parties, will know about it, and they will not use this part of the key for data encryption then.
So it is super secure, like super duper, like like it can't get more secure than that from the communication perspective.
I would call it ultra secure rather than super secure, but yes,
Yeah.
that's the power of quantum physics.
Oh yeah, okay, I agree. Let's leave. Let Doris have the word super, and with Toby, with you now we use ultra secure. I like that. Okay, ultra secure communication with quantum source, quantum science,
Quantum light source.
quantum light source. That is super interesting. Okay, now I'm with you. Going back to artificial material. As a material scientist, it's a bit confusing for me because you say you use semiconductors, but then you also say artificial material. Are you creating a new material or what is it?
Actually, I was talking of artificial atoms. So that is just a
Atoms, yeah.
comparison. You may know about natural atoms. If you have, for instance, let's say a hydrogen atom or a natrium atom, and you have it isolated, then you can observe quantum jumps. That is a electron which is moving around the atom, then it can jump between different energetic states. And the
Correct.
difference in the energy between these two states are left in photons, which are emitted by that single atom. Now, that's not really practical. We cannot put an isolated atom in a light bulb or something like that. And that's why we use semiconductor nanostructures to build something very similar, but we can control it much better. We have 5 degrees of control. That means we can design the properties of the photons emitted by these artificial atoms in solid state much better than for natural atoms.
That's what okay. So you go from the bulk material to nanoscale from the size perspective, dimensions perspective, and within those, then your ultimate goal is to control this photon emission. And so bulk material to a thin film nanostructure, and then within that there is the atom, and within the atom is then the electron. So there are multiple layers. Wow, this is so complex. Oh my god. Oh my god. It's good that you are doing it so we can have secure communication. Okay, that and what kind of materials do you use? As a material scientist, for me, it's always like, what material do you use? If you don't use natrium, which is sodium or hydrogen, you
Yeah.
mentioned semiconductors. You mean silicon or germanium? Like which
So
one
in
do you use?
principle, our group is interested in any uh, quantum emitter, which lives in the solid state, we call it. So we have a so-called quantum emitter toolbox, which is made of different species of artificial atoms. One of them are semiconductor quantum dots, where in this case we have, for instance, indium arsenide embedded, so small islands of indium arsenide embedded in a gallium arsenide matrix. Or you can also have indium phosphides in some matrix. Different combinations of different materials will give you different colors. And that's also how the growth people we are collaborating with, for instance, are able to give us samples which are emitting a telecom wavelength for quantum communication. But we are also interested in very different material systems like atomic design materials, quantum materials, which are maybe comparable with graphene, where you have really a single sheet atomic layer. And
Yeah.
also these materials enable us to extract single photons if
Mhm.
you have some confinement for electrons and holes in these structures. And
Mhm.
each of these different quantum emitter species has different advantages and disadvantages. So depending on the application you are in the end pursuing, and there's more than quantum communication alone, then you might choose a different type of quantum emitter.
Okay. And one last question on this, and then we will definitely move on. I mean, I can ask you so many questions, but one last question on this. Now we have optical fiber. When can we expect to have quantum internet, quantum secured internet? When is it possible for me to get that? Like, is it 5 years? How far away are we? Like 2 years, 20 years? Like, just timeline, just to, like, manage expectations. And this is not just on you, okay? And I'm not going to hold you accountable if you say 5 years. I'm not going to be like, okay, Toby, it's 2029. What is the status and all? I just want to get an indication as to how far away, how far in the future, or how short in the future can we expect the quantum internet?
Yes. So quantum internet, that's a huge mission, right? Maybe you can compare it with the things going on fusion experiments for harnessing energy in these large tokamak things. It's a mission for a decade and longer, and we have to build and develop a lot of building blocks which are not now working even in the laboratory space, which is a very controlled environment. So it will take extra time to also transfer that to field applications and actually deploy it in the fiber optical networks. But what you can actually get right now are really also from companies or research group as ours are these quantum light sources. These you can also buy as well. And there are also basically QKD systems, quantum communication systems, which make it possible that you set up a quantum secured link between your place and some other place, as long as you have a fiber optic link established between them. And these devices so far working also with heavily attenuated lasers. So if you don't have the expertise or capability to actually build a quantum light source, then you would use a laser and then attenuate it so heavily that you only get very few photons out of it. But that has also disadvantages for quantum communication, but it can be used for quantum secured communication already now.
Okay. So, like, the proper infrastructure change and blah 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 on a larger scale, that is, let's say, a decade or longer in the future. But what is already today available is securing, let's say, your own network, your own, like, I
Exactly.
can get it from you, like from your group or group similar to you. And how, like, is it like a charger? Is it a USB? Like, what is, and how much does it cost?
It's a bit more complicated than a small device. It's currently like 19-inch rack. So if you know from computer data centers, then you know that these are 19-inch wide, these racks. and you get these boxes in 19-inch flags, as well as the quantum light sources we are currently developing in my group. They are fitting into 19-inch rack, and that's why they are also capable of being field deployable. But there's potential, of course, to much more integrate this in the future.
Right. And you said 19-inch. Are these the twinkly lights, in the movies we see the server, when you go to the server room and there are rows and rows of these twinkly lights, and that's what you mean with the 19-inch rack,
Exactly, that's
right?
it. Right.
Okay, so 19-inch, for anyone who is more with the centimeter and meter system, it is close to 50 centimeters, so it is 48.26 centimeters, which is not that bad actually. And how much does it cost?
Yeah, maybe
You have to do the calculations.
it's still quite costly, right?
Mhm.
It's probably it is expensive, like you would if you think of buying a house, maybe it's in that order of magnitude.
Oh, the cost of security is really high at the moment. But on a serious note, it might make sense for, for universities or research institutes who are doing like super sensitive data analysis or sensitive research. For them, it might make sense, right? To make this investment, to have this, unless they have done it. Do you have that for your group?
You mean a startup?
Yeah, yeah. It's good to know that this is possible already today, and let's put it this way, it is already possible today, and it will only get more and more affordable in the next decade, or 15 years, or 2 decades or
Yes,
so,
of
right?
course. So it's depending on the technology you want to buy it, the price is not because it's the actual device is so expensive, but you have very low devices you are selling. So if more people buy it, then the price will drop.
Right. Let's talk about that, Toby, as a thing. After we stop recording, of course. Let's do it as our other brainstorm or thought experiments. I spent like almost half hour just understanding your research and asking so many other questions around that. What makes me also curious, Toby, is what has been the journey like to be leading quantum communication systems research group at the TU Berlin at the moment, being a group leader? How did that happen? Tell me about your career journey.
So the starting point was, of course, studying physics. After high school, I was wondering what should I do, and physics was always very interesting. My father was a physics teacher, so I decided for studying physics. That was in Würzburg, in Franconia, northern Bavaria, where
Mm.
I started from 2003 to 2009. And then I got so much interested in the exciting research that people were doing there that I decided also to, after my diploma thesis, to pursue a PhD. This I did with experimental research projects for 3 years in Würzburg. I
Mhm.
also had interesting research stays in Munich in a different group of Harald Weinfurter doing fancy quantum communication experiments in downtown Munich across rooftops. And then I decided actually in 2012 to move to Berlin and
Mhm.
joining the chair of Stefan Weizenstein at TU Berlin and
Mhm.
working as a postdoc. So I set up quantum optics experiments and I pursued writing my PhD thesis in parallel, which I finished in 2014, receiving
Mhm.
the PhD degree from University of Würzburg. So I kept this link until to date, and we have now also projects running again together with Würzburg as well. And
Yeah.
after the postdoc time and putting in more efforts in the research direction, 2018, I was able to attract a major grant, which was funded by the German Federal Ministry of Education and Research, BMBF, the Quantum Futur Initiative. That was a huge pile of money for a young researcher like me. And that enabled me actually to kickstart my own scientifically independent research group. And that made it possible for me to define my research agenda, which I'm now following for a bit more than 5 years.
And what does your father think about all of this, as he was a physics teacher, right? What does he think about you now leading a research group doing like hardcore physics?
He was always amazed by what I'm doing, and certainly very proud of achievements. Whenever I published something, he was very happy.
Aw, that is sweet. That is really sweet. That is so cool. Wow. Okay. Okay. And this to start your own research group, this is the BMBF funding that we are talking about here, right? I think my PhD work was also funded by BMBF. I would have to go back and check, but I think that it was also funded
Yeah,
by BMBF. That is quite interesting. It's really fascinating, and it's also good to know that you continue to have that collaboration with Würzburg or also with Munich even today, because I think that is the whole point of research, right? That you work together and you collaborate, and that is very interesting. Under the Microscope shall continue right after this short word from our sponsor.
So, have you ever thought about what would happen if your airline window popped out? Or if you could build a jetpack using only machine guns? Turns out you can, but you really, really shouldn't. Hi, I'm Jill Chacha, host of a podcast that's for weird people who like learning about weird stuff. It's called, well, That's Interesting, and it's a comedy science-y show that tells the story behind the facts because those stories are funny. Every Thursday, I tell the tale behind an odd new discovery, like how researchers found two mysterious structures surrounding Earth's core, or how it's actually possible to stop hiccups using a rectal massage. Yes, there's a story behind that. No pun intended. And I tell the story because storytelling is the perfect way to learn and remember. The facts are bizarre, the stories are epic, and the laughter is plentiful. So, join the flock and listen to Well, That's Interesting wherever you do podcasts.
I can ask you so many questions about your research. I can still go on and on about it. But if I ask you to pick one research project that you are most proud of, be it in Würzburg, Munich, now in Berlin, or even other places, could you pick one research project and explain it to us in simple words in the section we call In Other Words?
yes, of course. So actually, it's not a single research idea which made it through, but for me, it's actually this junior research group project which enabled me to kickstart my own group, and that has a lot of ingredients, right? As I mentioned in the beginning, for a junior research group, we have a quite broad view, so we are interested in really generating these single photon states or entangled photon states from artificial solid state atoms. And these we want to put into boxes, make them more practical, and then do actual protocols to encrypt data via optical fibers, and then scale this up to quantum networks, which we are currently doing at the campus of our university. It's really this endeavor of forming a group in the framework of such a junior research group. That is my big highlight.
Uh-huh. Yeah, I understand. I understand. I mean, I know it is also tough to pick one research project. It's like choose which kid is your favorite. Um, it's a tough one. What comes to your mind today, like right now? Do you have one?
We have a project which just started in January this year. That is a project within the so-called QNET initiative with the Fraunhofer Institute. And that project is about an intercity quantum communication link between two German cities, which have 75 kilometers of optical fibers. And in the end, we plan to do quantum communication protocols and run them on such a real-world setting. If we can transfer experiments, which we usually do in a very shielded lab environment, that we can transfer them out of the lab and actually deploy them in the field. That's a lot of fun for physicists to get out of the lab actually at some point, and that's also important for the transfer, of course.
Absolutely. You have to iron out the kinks to launch it to countrywide or worldwide sort of a thing. So it's QNET. Yeah, that's what the project is between the
The
two cities.
project is called QNET plus IC Link for Intercity Link.
God, you
It's a
physicists are
long
so.
acronym, right?
My God, you people are such nerds. Oh my God. With the acronyms, it's
Yeah.
ridiculous. Oh my God. It's funny. It's funny. It's fun. And it's also important. And thank you for answering that question. It definitely put pressure on you and it works. So
Yes.
I'm gonna remember that. That's really interesting. I would keep my eyes on this QNET plus whatever XYZ acronym that you just mentioned when the results and what we come up with or what
I
you.
mean, you can even join some field experiments, right? Can stay in touch. Then I give you a hint. If we have a measurement session between
Yes,
Jena and Erfurt, then you can join some measurements.
between Jena and Erfurt. Okay,
Yes, the
okay.
cities which are interlinked.
Let's talk about this. Jena and Erfurt, these are for people who are not familiar with your Germany's map. They're in the northwest-ish or ish. Sorry.
Northeast.
Northeast. Oops, sorry. Okay, northeast. Okay. Yeah, definitely. I want to join the field experiment for sure. I can create so much content around. Oh my God. Let's talk about that. Let's talk about that for sure. Okay, interesting. So, other than the field experiments and artificial isolation of atoms, if I am saying it correctly, it's clear to me that you really enjoy the research aspect. This is something that you're really passionate about. But what else do you like about being a scientist as a group leader? What else do you like, which you are like, oh wow, this is new. I did not expect this when I was thinking about starting my own group.
Yeah. So what is really, I think, a big advantage
Hmm?
is that I'm my own boss. That means I'm able to give the direction in the research I'm doing to
Mhm.
define this for my team and also make them interested of the topic I have. And no
Mhm.
one is telling me, Toby, you have to go this direction because we need to hit this milestone next month for our marketing meeting. But I can define the direction, and that's a big advantage, I believe. The other thing is, of course, that for me, it's a privilege, and I always tell this to my team members as well, a privilege to contribute to the knowledge of basically today, and also to the knowledge which is the basis for upcoming generations of scientists, firstly, but for specific applications which make it to the market. Also, of course, for the people in general and humanity. So that's really a huge benefit or asset, I would say, and is rewarding as well to contribute to the knowledge in general. And also a very important point for me is that we have exchanged with so many different people around the globe. So we have actually to travel also a lot still these days to communicate our research with other people and exchange about it. And that's also a wonderful thing because in the end, science is a language which is connecting across borders, across different cultures. There's the slope and bridging cultures, right? Science bridges cultures. And that's always nice. You get to a completely different place and you can immediately speak about your research with other people. And this is exchange is extremely important also to move ahead. If you are isolated with your research group, you can progress a bit, but you can progress much faster and further if you are doing this together with other researchers.
Mm-hmm. Yeah, definitely. I love all the points that you mentioned. Also, like you're your own boss. Like you get to decide what you work on, what direction to go with. It's like you're the CEO, but you've also mentioned a couple of times before, you are the CEO of your own company. You define how it goes, and yeah, definitely everything else. Also, like exchanging with people from around the world, really going and visiting people and their cultures and working together. It's a very it's definitely an advantage of being a scientist, and the side of scientists, like life as a scientist, that not a lot of people are aware of, and because they're like, oh yeah, scientists are only going in the lab and doing their work. No, we are traveling around the world, hello, and talking to so many people and working together to generate this wealth of scientific knowledge, and also communicating that to the people. That is definitely the case. It sounds all amazing, it sounds all awesome, and the highlights, like everything has been working out, everything has been great. But Toby, if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
All right. Yeah. So the first thing I have in mind actually is permanent position, because I'm still running on third-party funding, and my group is fully third-party funded. That means I have fixed-term contracts, and that's of course an important point to have a permanent position as a researcher on the professor level or equivalent. Because I'm not alone and I want to do research in a team, it's of course important that I would like also to offer permanent positions to other researchers, and that's typically a very difficult topic, also maybe especially in Germany, and that's why it would be great to have permanent positions also to offer to talented members of my team or people joining my team, to give them a permanent position as well and jointly pursue this research endeavor. And a third wish would be basically founding something like an own institute working on solid state quantum networking with, let's say, a couple of groups, maybe my own, with a lot of laboratory space, of course, and but also for 2 other groups working on material science and theoretical aspects of quantum information. So we have some joint facility to really push things forward in the field and focusing on these challenges. That would be a really nice thing. And I love fancy new buildings with nice laboratories, because at German universities, you not always have new buildings around.
Yeah, definitely. And to do cutting edge research, you need cutting edge facilities and environments. Definitely. Very realistic wishes, I must say. I'm pretty sure soon in the future you're going to get a permanent position for yourself at a professor level, and I guess that also comes with these 2 permanent positions or at least 2 permanent positions for the members, because that is something that is always like that is the downside of being the CEO of your own company, that you also have to make sure that the revenue is coming in so that you can keep the team and grow the team, and also provide the team with the right resources or
Indeed.
fancy machines or whatsoever, everything that is needed, of course. And research institute, solid state quantum information and networking, let's talk about that.
Not bad, right?
Sorry?
Not bad, right?
Not bad. You have a plan. I love that. That is really cool. You have a plan, you have a goal in mind, and I'm pretty sure these wishes will come true. Even if I don't have the power to make your wishes come true, I'm sure you have the power to make your wishes come true. Wow, that was such a deep and philosophical. I'm proud of you. That's really cool, Toby. This has been amazing. I feel like I see a very different side of you compared to what I'm used to do, what I'm familiar with. This is the researcher in you, the group leader in you, and the scientist in you, which has been amazing. Before I let you go, I want you to tell us all what can the followers of the Real Scientist Nano Twitter account expect in the week that you're taking over the account? Because featuring on the podcast is one, and the second part of Under the Microscope project is, of course, you get the keys to the Real Scientist Nano Twitter account, which has more than 3,000 followers. Woohoo! No pressure. For an entire week, this makes you also accessible to the people, to the followers, which is not possible usually with the podcast or a video recorded. So, what can the followers of Real Scientist Nano expect in the week that you're taking over the account?
Yes, so firstly, I'm glad of this opportunity, of course, for this extended reach. I'm looking forward to it. And we will start with introducing myself and my team, which is probably something which will go throughout the week, actually, within one thread. I want to introduce, that would also be on Monday, the quantum ecosystem in Berlin, because we have a very rich environment here with companies and a lot of institutes which are diving into the photonic quantum technologies topics, and that I would like also to highlight. And during the week, we will move on with highlighting our lab work, how actually look our labs like, and what we are doing in these experiments. Maybe we will have some live experiments showing or proving that we have single photons at hand in our laboratories. And towards the end of the week, it's more going in the direction of the Quantum Outreach project you're very familiar with. So I will have a tech check on Thursday to prepare things for the Sunday, actually. On Friday, a very big topic will be a PhD defense of one of my first students graduating. That will certainly be a highlight as well. And Saturday, probably some things about what I'm doing outside university. Let's see how the weather will be, whether we can go into the nature. And Sunday, the kickoff of the Quantum project will be a lot of posts certainly about.
That is awesome. That is awesome. This is an action-packed week that we are expecting. For the PhD defense, are you working on the PhD hat as well?
Of course, my team is working on this, and I'm contributing what I can. It's not only about the hat, but also a few other items, of course. Yes, there are lots of things to organize because it's a very interesting PhD project having an end, and then we have to celebrate, of course, together.
Of course. That's gonna be amazing. And ending the week with a big bang with the sticker ceremony, as I like to call it, for
Yes.
Contour. That's gonna be so much fun. Oh my god. That's gonna be so much fun. Awesome. Then this is like I cannot wait to follow your tweets and also be part of that, at least on the last day, as I will also be in Berlin for the sticker ceremony. What are we calling it? Contour kickoff. Like officially it's Contour kickoff.
Yes, exactly. Contour kickoff.
Contour kickoff. 12 months, 12 labs, one source. Thank you very much, Toby. This has been super wonderful, and I'm very, very happy that I finally got you on Under the Microscope, and also looking forward to having you on Real Scientist Nano. Thank you.
Thank you so much, Pranoti. It was lovely to join you.
Thank you everyone for watching and listening to Under the Microscope. Your support, as I mentioned, means a lot to us. Make sure to share this episode with your network, with whoever you think will benefit from it and learn from it. This helps us grow the community of scientists who are interested in materials and nanoscience or even quantum science in this particular case. I'm your host, Pranoti, and see you at the next episode. Bye.
Hi, fancy folks. Welcome to Lux Sci, where we make science fun, approachable, and most of all, fancy. I'm Dr. Lex, former microbiologist, current global health consultant, and enthusiast of all the finer things in life. I'm often joined here by my husband, electrical engineer, inventor, and our audio engineer, Dr. Demos. In this podcast, we take listeners on a journey into the microscopic worlds of luxury items and unravel the fascinating intersection of science and opulence. From how bubbles form in champagne, to the molecular forces that harden clay in a kiln, to the amount of thrust needed to send a rocket to space. No luxurious topic is safe from our insatiable curiosity. We're on a mission to demystify science and show how it drives the world around us. No PhD or lab coat required. So if you've ever wondered how science and luxury seamlessly intertwine, join us as we uncover untold stories, hidden marvels, and the inner workings of scientific discovery and sophistication. Along the way, we'll also chat with amazing scientists and artisans, so subscribe now and let the exploration begin.